Okay, let's continue. So as the student said, this is a formula slides with a lot of formulas. We went through these slides on Friday. Let's quickly go over the slides again because we're going to utilize a lot of formulas from these slides. So this slide is talking about the long line model, but long line model is considered as the most accurate model. It's not just applied to lines which are very long. It actually can be applied to any short line or medium line. Just for short line, medium line, we have a simpler model. So we don't have to utilize this model. So for instance, if the line is very short or shorter than 250 kilometer, you can utilize the actual, let me see. You can utilize the actual impedance of the line and actual admittance to the line. But when the line is longer than 250 kilometers, so you have to utilize the Z prime and the Y prime to correct the actual impedance and admittance. For the total admittance, you split into half and put two halves on both ends. This slide is about the lossless line. Lossless line means we can ignore any resistance or conductance. Resistance is actually the connected in series with the inductance. Conductance is actually connected in parallel with admittance to the ground. Oh, yeah. So when we ignore the resistance and the conductance, so only consider the inductance of the line and capacitance of the line to the ground. ZC is called a surge impedance. It's originally defined as the square root of the Z divided by Y. Z is the impedance per unit length, and Y is the admittance per unit length. So if we ignore the resistance of the line, so it will be simply equal to the square root of L divided by C. L is the inductance per unit length. C is the capacitance per unit length, which are the two parameters we calculated from previous section, from line parameter sections. So gamma is defined to be the square root of product of Z and Y. When we ignore R and G, so both Z and Y will be a purely imaginary number. So the square root will become a purely imaginary number as well. So the imaginary part is called beta. And so if we ignore the resistance and conductance of lines, so gamma will be simply just J omega times the square root of the product of L and C. So it's a purely imaginary. Because the gamma is purely imaginary, so when we plug into that imaginary number to the accurate formula for long line, so anywhere we see the hyperbolic function, which will become sine and cosine function. So which means the cos gam s will which is cos j beta s. So that is simply become cosine beta x. And sinh gamma s will simply become j times sine beta x. So that helps us largely simplify the model. So the Z prime, which is the corrected total impedance of the line, now become a j times ZC times sine beta L. So that become just a purely imaginary number. It just reflects the equivalent total reactance of line. So ZC times sine beta L represent the total inductive reactance of the line. The half of Y prime right now become another imaginary number. So J times the 1 over ZC times tangent half of beta L. So this part just represent the total admittance to the ground. So we can still take this transformation. So we'll have those coefficients calculated by those expressions. We utilize this model to study two special contingencies. One is the short circuit at the receiving end when receiving end voltage is 0. So the conclusion is definitely when you have short circuit at receiving end, the short circuit current due to the fault can be very high. That high current will also impact the current on the source. So if you don't disconnect the line, this fault current will impact the source. So that can be, for instance, if the line is not very long, it's only just 80 kilometer, this fault current will be about 99.5% of the fault current at the fault point. Okay, so which is very high. So even you have a long line, like 400 kilometer, so that will make the beta L be roughly 30 degrees. So the fault current on the source will still be more than 85%. It's still quite high. So which means when you have short circuit on the receiving end, you need to use the protection to disconnect the line, to disconnect the line from the fault, to isolate the fault, such as the impact on the source can be limited, can be avoided. When you have open circuit on the receiving end, so the load current will become 0, which seems to be okay because there's no fault, no short circuit. But what happens is that can raise the voltage on the receiving end to be higher than the limit. So especially for long line, when you open the circuit on the receiving end, the receiving end voltage can be 15% higher than the source voltage. So that can trigger some over voltage protection, because usually we expect the transmission line to operate within roughly 5% violation. So which means if you operate 500 kV lines, you want to operate to maintain the voltage everywhere within the range of 475 to 525, roughly 5% of the violation. But 15% is too high to trigger some protection. So that's just quick going through of what we learned from last week. So this is the last slides we talk about at the end of the Friday lecture. So this just to introduce a concept which is called surge impedance loading or surge impedance load. It's just exactly the load when the load impedance is equal to the surge impedance. So surge impedance, if we ignore the loss of the line, so which is simply defined as the square root of L divided by C. A surge impedance is a real number. It's not a complex number. Even we call it impedance because we just consider this one as ideal load impedance at power factor exactly 1. So it doesn't have a reactance, doesn't have a reactive power. So this one will be completely just CC. So if we make the load impedance be equal to surge impedance, when we calculate the load, so that load is just called surge impedance loading or surge impedance load. So when we calculate the voltage along the transmission line, and we found out everywhere the voltage will have the same magnitude, which is same as the load voltage. The only difference is with the angle. So by changing the distance to the load, so this angle can change, but the magnitude of the voltage will be same everywhere. So current also have the same magnitude and with the same angle. So even you measure the voltage phasors, current phasor at any point on the line. So the voltage and current phasor exactly parallel. So they point into the same direction, which means the fault factor along the line everywhere will be same. So for this case will be 1. So you have a unity power factor everywhere. So that's why we can consider surge impedance load as the ideal load, right? So if your operator, every line of your system is powering surge impedance load, that's perfect. Okay, so voltage everywhere will be same. For the line operating at 500 kV, everywhere will be 500 kV. 220 kV, everywhere will be 220 kV. So that's perfect, but that usually cannot happen in reality. But we still can utilize surge impedance load or surge impedance as index to evaluate what the ideal load is for specific line. Okay, so if your actual load is higher than this load, which means you need to provide some reactive power. If it's lower than this load, you need to consume some reactive power. Because when you operate at surge impedance load, the power factor everywhere will be same, which means the reactive power consumed by the line itself is completely provided by the reactive power supplied by the line. Because the line has both inductance, which will consume some reactive power. It also has capacitance, which will provide some reactive power. So at any segment of the line, so the reactive power consumed by the inductance will completely equal to the compressed power, the reactive power provided by the line, by the capacitance of the line. So we'll have this equation hold everywhere along the line. So that's why it can be a very useful measure for the line. If the load is much higher surge impedance load, then you need to have shunt capacitor, because for this case, the voltage on the receiving end will be lower than the sending end. If this load is much higher than surge impedance load, you need to add some shunt capacitor to support the voltage at the receiving end. On the other end, if you have the load is much smaller than surge impedance load, you may need to have shunt reactor to limit the overvoltage of the line. So that actually explains what happened on this slides. So when you have open circuit, which means load is equal to 0. So when the line is very long, so the voltage will be higher, will be much higher than the source voltage. So you need to add shunt capacitor to limit the voltage. Okay, so those are what we know from Friday. And this is a picture from the textbook, which just describe how the voltage change from a sending end to the receiving end. So now we just assume there's a line which is about a 600 kilometer, and this end will be the sending end. This end will be receiving end. So when you have surge impedance load on receiving end, the voltage for this case is 500 kV line. So it will be flat everywhere along the line. The voltage will be same. If you measure the voltage at any point, the magnitude will be same, exactly 500. So if you have the load, usually the load of the line is higher than the surge impedance load. So for instance, if you operate at the rated load, so near the sending end, you still have 500, but when you become far from the sending end, the voltage will drop. It can become very low. So if you don't provide some capacitor to support the voltage can be much lower than the rated voltage. So if you open the circuit, so when you open the circuit, and the receiving end will have a higher voltage, it can become much higher than the source voltage. And when you have short circuit, and the voltage can be roughly linearly decreasing to 0. At the point of the short circuit, the voltage becomes 0, become the ground potential. Okay, so that's what happened. Another table which is useful is to show the surge impedance and the surge impedance load for at different voltage level for some typical transmission line. So for instance, if you operate 230 kV, because the surge impedance not only depend on L and C, it doesn't depend on the length. So for 230 kV line, if you know the typical size of conductor, you can calculate the geometric mean radius of the conductor, and you also, if you know the spacing for 230 kV line and what tower the tower may look like, so you know the geometric mean distance So you know GMD and GMR, so actually can calculate L and C. When you after you calculate L and C, so surge impedance just simply equal to L divided by C, right? It doesn't depend on the length of line. So you will know the surge impedance. And because you know the voltage, you can calculate the surge impedance load. So for 230 kV line, the surge impedance load, or in other words, ideal load will be 140 megawatt. So if you use this voltage line to power 140 megawatt, the voltage everywhere will be perfect, okay? But if your load increase to double, so you will expect to see the voltage on the receiving end to be lower. If you open the line for maintenance, you will have higher voltage. Okay, so right now, if you need to power a much higher load than 140 megawatt. For instance, if you want to power around 400 megawatt, so it's better you have a higher voltage line, 345 kV. Okay, then you can maintain at the new surge impedance loading. If you want to power 1 gigawatt power, it's better you have a 500 kV. But usually we know when we define the voltage level, we'll not just check the loading, but nominal load. There's many other considerations. So which means when you operate very high voltage, usually for some condition, you don't have to power this much of load. You may only just power load much less than this value. So for high voltage line, you will more likely to see some over voltage issue. Okay. So if your load is lower than surge impedance load. This table also gave you some other typical value, which is very useful. So if you want to do some calculation without knowing the details of the tower design of the conductor, but you want to roughly get the idea about LC resistance, surge impedance, loading, alpha beta value. So actually you can check this table. So for instance, if we check beta value, so you see every line has almost exactly same beta value, which is 0.0013. Okay, very close. So that sounds pretty strange. Why are they all the same? Very close. We'll try to explain in this lecture. Okay. So next, we want to utilize this most accurate long line model to calculate complex power flow. We have derived the complex power flow formulas many times, right? We start from just a single circuit with single impedance. We calculate the complex power flow sent from the one end and received at the other end. Then we move to a three-phase line. We also derive the complex power flow. But now we have more accurate formula for any long line model. So we can try use this accurate formula to rederive the complex power. So we'll start from this transformation from the receiving end voltage and current phasor to the sending end voltage and current phasor. From the first line of the matrix, and we can know the source voltage is just a linear combination of the voltage and the currents at the receiving end, and there are two coefficients A and B. So A is actually cos gamma L. So if you know the Z prime, the Y prime, which are corrected impedance and admittance of the line, so you actually can calculate A. B is simply the Z prime. So then we can know the load current can be represented by function of the linear function of Vs and Vr, utilizing the coefficient A and B. Similarly, we can utilize the inverse transformation from the source voltage and current to the load voltage and current. Okay, so by utilizing also the first row of the matrix, so we'll have the VR be equal to a linear combination of the VS and IS, because for this case, this model, we take a pi model. So we take a pi model, which is symmetric. So that will make A and D be equal. So which means D is also equal to A. And we can get this formula to calculate S, also depending on the voltage. So now we're ready to derive the formula to calculate three-phase compressed power from the source, and also the compressed power from received from the load. So they will be different because there are some shunt branches going to the ground, so which will change the compressed power. So if we use line to a neutral voltage and line current, and we need to multiply the power by 3 to give you three-phase compressed power. And here we use the load voltage as the reference with angle 0, and the source voltage will have angle delta. So if you want to send the positive active power from left to right, delta has to be positive, right? Delta need to be higher than 0 in order to deliver active power from the left to right. So if you want to deliver reactive power from left to right, you need to have the VS be higher than VR, right? That's what we learned from starting from section B. So next we just plug in the expression we get about IR and IS. So we'll have a formula for the compressed power only depend on the voltage phasors on both sides. So next, you just need to rewrite each compressed number or its conjugated value in the polar form with magnitude and angle. Okay, so we know the VS has angle delta. For B is actually a compressed number. So we can just represent it at B and with certain angle, we just call B angle. But this case is a conjugated value, so it can be just a negative value, right? So we can do similar thing, and we'll have, we replace every compressed number by the polar form. Similarly, for the compressed power from the receiving end, so this is the current for the IR, and then we rewrite every complex number in the polar form. We have this one. So this is very complex, and it's not required to memorize those two equations. So I couldn't do this either. So, but you just know this is the most accurate formula. If we want to utilize the transformation ABCD to calculate the compressed power. But we can only study the special case for lossless line. So for lossless line, A will be simply cos M beta L. B will be J times surge impedance times sine beta L. So I mentioned, so this one represents equivalent reactance of the line. So we just call it S prime. X is actually the total reactance of line. So for this case, if we ignore the resistance, so actual reactance will be X, and we add a prime because it's going to be S multiplied by a factor, right? That factor is very close to 1 for medium and short line. So S prime will be just equivalent total reactance of the line. So the B will be JS prime. So if we plug in this A and this B into the top two formulas, and we know for the angle of A will be 0, angle of B will be 90 degrees. Okay. So we can largely simplify the formula and get the real part of the sending and compressed power, receiving and compressed power will be equal because there's no loss on the line. So the active power sent from the left will be completely received from the right, which will be this formula. So the form look very familiar to us because we have derived similar formula several times, starting from section number 2. But so delta is the angle difference, right? Sine delta angle difference. Then, so those two are just line-to-line voltage magnitude. And this one represents the total readiness. So it's the x prime, not the actual x, because we need to make some correction if the line is very long. For the reactive power, we have two formulas because the line will consume some reactive power. It may also provide some reactive power. So the Q from the left and is different from the Q on the right. So if we compare those three formulas to the formulas we derived in back to chapter 2 for very simple circuit. So in chapter 2, we have a P12 equals the product of V1, V2 divided by the total readiness, and then multiplied by sine delta, the angle difference. Okay, so if you compare those two completely in the same form, the only difference is this x prime, not actual x. So which means the original formula in chapter 2 can still work. We just need to correct x into x prime by multiplying x by a factor, by multiplying this factor. So this factor will be close to 1 when the line is not very long. For two reactive power, we made more corrections. First, we still need to we definitely need to correct the actual readiness into the x prime. We also need to add those two factors there, cosine beta L. Beta is actually the imaginary part of gamma. Okay, L is the distance. So beta we know is around 0.0013, right? For any line, will be roughly this value, or very close to this value. But L can change. So when the L is very small, beta L will be close to 0. Then cosine beta L will be around 1. So that will completely become the formula from chapter 2. But when the line is very long and cosine beta L is not 1, and we need to utilize those two more accurate formula to calculate reactive power. Okay, any question? All right, so next we can talk about the transmission capacity of the line. So for each line, so we can connect we can split the line into many segments. So each segment will be connected to the neighboring segments through a tower. So towers such as those two towers, and so usually you won't be able to see the line will be will be completely straight. So there will be a sag, which means there will be some at the middle point, there will be closer to the ground. But usually we want to control that sag. We don't want that sag to be too large. So depend on the distance to the trees or houses under the line. So we want to make a safe clearance above those buildings and the trees. So otherwise they can cause some short circuit. The sag will change with the temperature of the line. So when the temperature go up, the sag will increase because the length of line will increase. So then we need to give each line some capacity of the current. We just call it current carrying capacity. We use the I thermal to indicate the limit of current. So if we know this limit, depend on the line and the clearance to the building and trees, and if we know the voltage level, we can calculate the thermal loading limit in terms of the apparent power. So which is basically just the thermal limit of the in current multiplied by the line-to-line voltage, the rated voltage, then multiplied by the square root of 3. So this is because we are calculating the three-phase power. So for apparent power, it will be the apparent power for each phase multiplied by 3. And here we utilize line-to-line voltage, so which is the root of square root of 3 times the line to the neutral voltage, right? And so the root of 3 and this root of 3 together, multiplication will be 3. So that will be 3 times of apparent power of each phase. So in this formula, all variables, all values are real. They're not complex number. That's will be the highest limit we define for each line. In reality, the actual loading will never reach that thermal limit unless there's some really big sag, and the line is overloaded for extended time, and the sag is increased, and so that can happen in some extreme conditions. But in normal conditions, we usually compare the loading to the steady state stability limit. For instance, if we calculate three-phase active power from the previous slides, will be this formula. We want to figure out the highest value of the active power of the line. So first we divide, because here we use the line-to-line voltage on the sending end and the receiving end. We divide each one by the line-to-line voltage, the rated value. X prime is equal to CC multiplied by sine beta L. And to cancel the two rated line-to-line voltage, we also multiply the formula by the line-to-line voltage squared. Okay. Then we can change this one to the per unit value and this one to the per unit value. The formula will become per unit voltage on the sending end, per unit voltage on the receiving end. So here is the angle difference and this sine beta L, and so this part is exactly the just third impedance load. So we'll have another more useful formula to, if we know the per unit voltage, we know third impedance load, and we know the angle difference, and also the length of line. So we can utilize this formula to calculate the active power. Okay, next. So this is like sine function. Okay, beta is around 0.0013, very small value, and L can change. We know this value cannot reach to 2 pi, because if a sine 2 pi, if it becomes 2 pi, if this one reach to 2 pi, sine 2 pi will become 0. So that will make this formula not valid. Okay, so we will assume the beta L will have some upper limit, which is 2 pi. If the beta L as angle has upper limit 2 pi, which means the L will have some limit, we call it lambda. We just define the lambda as the limit of L. So when lambda is equal, L equals to lambda, to the upper limit, lambda divided by L divided by lambda will become 1. So this denominator will become 0, right? So that will cause some singularity. So we just guess the lines of line can never reach this upper limit lambda. And this lambda must have some physical meaning, and we try to figure that out. Okay, so let's assume beta L equals the 2 pi times L divided by lambda, and if the beta is equal to 0.0013, lambda will be equal to 2 pi divided by beta. the lambda will be 5,000 kilometer. So the length of the line will have a limit around 5,000 kilometers. On the textbook, the lambda is called the wavelength of the line. Dr. will explain why we call it a wavelength. So now by this slide, we still want to find out the steady state limit of the line. So which is the upper limit of the IT power. So we know the IT power is a function of angle, basically sine function of angle. So it will have the maximum value for the power. So when the angle take a 90 degree. So when the angle take a 30 degree, the power is half of the maximum value. Okay, so we just defined the theoretical limit of the three-phase IT power as the power at 90 degree, when the angle take 90 degree. So we'll just replace this sign delta by 1. So this will become the definition of the theoretical limit, which is same as in this formula we replace the sign delta by 1. Okay, so we can have either this formula or this formula to calculate the theoretical limit. But in reality, usually the angle separation between the two ends of line will never reach 90 degree. So it's more practical to consider a smaller angle at 30 degree. So when delta is at 30 degree, so we can define practical line loadability or limit at 30 degree. So that will be only just half of the theoretical limit. So this is a more practical limit for the line loading. All right, so we want to explain what that lambda is. I mentioned that the lambda has some physical meaning as the wavelength of something. So when we call it wavelength, which means it represents some wave. Let's talk about the waves. Either a voltage wave or current wave. Let's just use instantaneous voltage as one example to study the wave. We know when we define instantaneous voltage at a bus, which is a function of time, right? There's only just one variable, single variable t. So when t change, the voltage will change. So instantaneous voltage is defined as the peak value, which is the square root of RMS value multiplied by cosine function, right? So go back to the beginning of the section number 2. When we introduce the instantaneous voltage, we assume some frequency, omega, which is 377 reading per second. We also have assumed some initial phase. Okay, so if we define all those parameters, then we have accurate formula for the instantaneous voltage. For this cosine function, there's another way we can represent this cosine function. We can treat it as the real part of a complex number in the exponential function form. So we leave the square root of 2 outside, and so inside we have it's a complex number with the magnitude and also this angle, this phase is changing with time. And then we introduce the concept of phasor, because we don't want to write this complex expression. We know the omega will be constant, okay, in steady state condition. And so we want to keep only the most important information, which is the RMS value of voltage and also this initial phase. So only those two informations, pieces of information are critical. Once we know the absolute V and the theta, we can construct a phasor. And from this phasor, we can go back to the original accurate formula. We just need to multiply the RMS value by square root of 2 and also construct this cosine function, right, by adding omega t. So that's how we propose the phasor's representation to simplify the instantaneous voltage. Okay. So those two representations are equivalent to each other in steady state conditions. All right, so now we move to the voltage along a transmission line. So if we use the receiving end as a reference as origin of the coordinates, we need to measure the distance to the receiving end. So we need to add a new variable x. So now the voltage along the line will become a function of both time and the distance to the receiving end. And when we try to solve the voltage along the line, and in the phasor representation, we use capital V. Remember, we derive this general solution for the second order differential equation on the line, which has two exponential functions depending on the two eigenvalues, right? So then we utilize the boundary condition to solve A1, A2. We actually derive the more accurate formula for voltage. Then we calculate the voltage when X equals L. On the sending end, we have the more accurate formula about the voltage than the transformation. So this expression is still in phasor domain. It's not about instantaneous value. So how can we find instantaneous value similar to this one for any point of the line? Okay, so you can imagine we'll have something like this one, right? So in order to get the formula for the instantaneous voltage along the line, we have to understand what happened in this transformation. Okay, so first we need to make sure the phasor can be represented in this form. We has absolute value and also the angle. So we need to figure out the angle for this expression. So we have two items. The first item, the magnitude will be the product of the A1, the magnitude of A1, and then the magnitude of the E gamma X. So E gamma X, gamma is equal to alpha plus J beta. Okay, so E gamma S will be E alpha X multiplied by E J. The exponent is J beta X. So J beta S will move to the angle. And also, if A1 is complex number, A1 also have angle A1. So this one will have the first item to be the absolute value, and here will be angle. So which is similar to this form. Will be similar to this expression. Then we can try to guess what this instantaneous voltage is by adding definitely this the square root of 2 and also the cosine and omega t, right? We can easily create instantaneous value starting from the first item, the right. Similarly, the blue item comes from the A2 times E negative gamma X. So the magnitude will be the magnitude of E2 and times E negative alpha X. And angle will be one angle will come from the negative beta S, another angle will come from A2. So this one can also be equivalent to, we can just call it E1. Okay. which means the voltage along the line at any point of x as function of x. So that has two items. Each one can be represented in the phasor form, and from the phasor form we can find their accurate formula for the instantaneous voltage. So we need to multiply by square root of 2, and we need to consider omega t, and also you need to introduce the cosine function. So basically, we just square root of 2 multiplied by the voltage. Then we plug into the cosine function. Right? So similarly for the other item, we can do the same thing. We can get instantaneous voltage. So let's see what happened. Okay. So the V1 will be simply just this one. We'll have this is square root of 2, and this is the manual voltage, and this is the cosine function. So for the second one, we'll have this one. So what are those functions? So each function has variables including both time and distance. So the first one represents incident wave from the left to right. So if left means the sending end, right means the receiving end. The second wave indicates a reflected wave from the right to left. So you can assume some wave sent from the source to the load, and then the load will reflect the wave back to the source. So if we utilize the example from the slide number 10, on the slide number 10, we do a calculation for a long line model, right? We for 225 miles line, so we have those A1, A2 solved. So now we can utilize those values. So we utilize that A1, A2, just plug into those two formulas to see what happened. We can draw those two functions. So there are three curves. There's the right one indicate just A1, blue one indicate A2, and also we calculate the black curve indicate the sum. So if we select the curve, if we let the curve to move, let's see, doesn't. Okay. So you see the right curve is moving from left to right. Blue curve is moving from right to left. And the total, which is black, is still from left to right because the blue curve is much lower, has much lower magnitude than right. So this speed has been slowed down because the actual speed can be extremely fast. So in general, the A1 has bigger magnitude than A2 because if we consider third impedance load, so the blue one will be close to 0 because if the load is currently third impedance load, this one will become exactly VR. So this A2 will become 0, and if this one becomes third impedance load, this is VR, and this one will become just VR. Okay, so if the line is powering third impedance load, A2 will be 0, A1 will be load voltage. So which means on this chart, the blue one will become 0, and the red and black will be the same curve moving from left to right. All right, so the next question will be, what are those waves? We will explain this one on Wednesday. Yeah. No. No. That's